As I said before, the martensite is a very hard and brittle phase, and it contains a lot of internal stresses. Therefore, the martensite cannot be used as it is. But how to use it then? Yes, we can actually temper the material, make a heat treatment again. And that is done normally in the range from 250 up to 650 degrees. And then you get a material that has a higher ductility and a lower hardness. That's one of the tricks with steel, that you can actually adjust the combination of ductility and hardness by choosing the tempering temperature. So if you temper at a high temperature, also after long times, you will get a soft material with low hardness. But if you make a short tempering, or you do it at a lower temperature, you will get a harder material, but somewhat more useful than the martensitic structure, of course. So we look into what is really happening during the tempering now. We will start looking at the phase diagram again. What we have done now is that we have made a hardening. It means that we have started in this austenite region, and then we have quickly quenched the material down to room temperature, either in water or maybe in oil. And then we have obtained a martensitic structure. The martensitic structure is actually a ferrite with a carbon content somewhere here, with a higher carbon content than actually can be solved into the normal ferrite matrix. So what happens now when we want to temper this martensitic structure? We increase the temperature and come up into this area somewhere. And then we see in the phase diagram that we are in the region here where we should have ferrite with this carbon content, and we should have cementite with a carbon content of 6.7%. And what's going to happen? What's going to happen is that we're going to precipitate cementite particles. So carbon is going to go from the martensitic positions, and then we go to the cementite particles. It means that we get small cementite particles, and around them there will be ferrite with low carbon content. And those areas around the particles will be soft, while the particles in themselves are hard. But this means that the total effect of the material is that when the areas around the particles getting soft and getting larger and larger, the total material is going to get more soft. We get better ductility, but we lose some of the hardness. So we can choose by what temperature we are going to do this tempering at, and we can also partly choose the time, but normally we choose temperature or keep the time constant, roughly half an hour or 1 hour. And at high temperatures, what's going to happen is that we get large areas with low carbon content, and then we get larger particles. So if we wait for a long time, we get larger particles, and the whole matrix is going to be soft ferrite. And if you go really long time, we get something that is called spheroidite. It means that we start getting relatively large and round particles of cementite and a very soft matrix. Then we have got a really soft material. So we can choose all alternatives here. Short time at low temperatures, we still keep a lot of the hardness, but start getting the material more useful by giving it some ductility. Or we can increase the temperature and get some intermediate appropriate combination of ductility and hardness. Or we can go for a high temperature a long time and get spheroidite, get a real soft material. It might be rather good for wear purposes with these hard particles within it. It's also good to have if you want to really deform it at cold temperature. So let's look at some pictures of how the hardness changed by temperature and different carbon contents. Here we now see some tempering curves for some different steels. And what we see here is the hardness on this axis and the tempering temperature here. In this case, the tempering has been going on for 30 minutes at each of these temperatures. And we can also see here the effect of different carbon contents in the steel. This is a low alloyed carbon steel. And this curve is for 0.30% carbon. This is for 0.50, 0.70 and 1% carbon. So we can see here the starting hardness in in the martensite that it increases strongly with carbon content. So here we have a very, very hard martensite. If the carbon contents are low, below 0.2, the martensite is not so very hard. It actually can be acceptable and used. But anyway, if you have these type of steels, they need to be tempered. And then we see what happens if you temper it at different temperatures. We see that the hardness goes down rather strongly for the high carbon content alloys. In half an hour at 600 degrees, and we are down here at 300 Vickers. But this is not the sphaerite. If you really should continue to do this at maybe 650 and 700 degrees and go on for about 20 hours, then we will get to the good sphaerite, and we can assume that the curve still continues to go down somewhat. And then, before we get this type of structure, this is a sphaerite structure. And what we see here is the particles of cementite. They are rather large and they are well rounded. And the matrix here around them is ferrite with low carbon content. Therefore, there is a very soft matrix with these hard round particles. So here we have a really ductile material. Interesting to note here is that this is an equilibrium structure for a long time at high temperature. And this is what we find in this two-phase region after a long time. The particles grow in size. Actually, if you also should start with a structure that contains ferrite and pearlite, that is, if we have got a structure that has cooled down slowly, we would also end up with the same type of structure. We would get this type of sphaerite, because after a while the lamella in the pearlite are going to be rounded and they're going to grow. So after a long time we get the same structure, as this is the equilibrium in this system at this temperature and at this composition. This is a structure then that is very suitable for machining and forming in cold shape.